Alright, Chili here. Welcome back to the SSE Optimization series. And today we are going to actually get down to some processing. Now the first filter, the first effect that we are going to be tackling is a fade effect, fading to black, which is simply just blending whatever's on the back buffer with the color black. Now we've done blending before. We've done it in alpha blending, and we've also tackled the same concept when we were texturing triangles. So let's just do a quick review of that though. Now alpha blending in general is just a linear interpolation between two values, where if alpha is equal to 0, right, you're going to get all color 2, and if alpha is equal to 1, you're going to get all color 1. And if alpha is equal to 0.5, you're going to get an equal blend between the two. So what we want to do here is we want to reformulate this in such a way that we can do it with just all integer math. And this works because, of course, we're multiplying C1 by the fraction of alpha over 255. And that fraction converted to decimal will be a fraction between 0 and 1. Of course, you have to be mindful that the order of operation has to be multiply and then divide, because if you divide first and multiply, you're going to get all fucked up. Now we're going to make one more slight adjustment. Dividing is a slow operation, and if we can avoid it, that would make our lives much easier. If we instead of dividing by 255, if we divide by 256, this will make the operation a hell of a lot faster. Because dividing by a power of 2, right, 256 is just 2 to the 8. So dividing by a power of 2 can be implemented by bit shifting. Shifting to the right 8-bit positions is equivalent to dividing by 256. So by altering our formula slightly, we're going to be off by a very little bit. We're probably going to be off by about 0.4%, give or take. We're introducing a bit of error into our calculation. But by making this slight trade-off, compromise, I guess, we can increase our processing speed quite a bit. And I'll show you how that works out later on. Now, when we're fading, C2 is equal to 0, so this gets canceled out. Kind of forgot to mention that. I hope it was obvious. If not, well, I guess you know now, because I just told you. So we're going to do it first with the non-optimized, just standard C, and then afterwards we're going to see how it looks in C or in SSE. So here's a standard fade here. We load a color, and then we do what I just showed you on the whiteboard. We multiply by alpha, and we divide by 256. Now, I know I told you that dividing is slow and we'd rather right shift, but the compiler is smart enough to know that if you're dividing by 256, it can just do a right shift and save a lot of instruction. Or a lot of clock cycles, I should say. So let's build this. We're gonna, well, we don't want that in there. So I believe it was fade, and we need an alpha value, so we're gonna use alpha. Now alpha in this test bench is controlled by the mouse wheel, so we can control our alpha value using the mouse wheel. And we'll build this, and I'll make sure we're in release mode, and then I'll run the motherfucker. So here we go. I can use the mouse wheel. I can fade in, go too far, and go roll over the other way and go back to black. And so that works fine. And let's look at our execution time. So holy shit, it takes about 5 milliseconds, 5,000 microseconds to fade the screen, compared to 100 microseconds to fill it. So 50 times slower. Yeah, it's 50 times increase over just a standard move. Seems pretty bad. Now I just want to do one short double underscore decal spec, no inline. I just want to show you guys and make sure that this is actually being optimized here. So we're going to run that. And we're going to go to the disassembly. And you'll see down here, once you get into the body of the loop, that we are shifting right. This is shift algebraic right by 8. So we are shifting right a bunch by 8. So that's where our division. There is no division. There's multiplication. There's no division instruction being called. It's all shifting. So we can see that the optimization is being carried out, but we're still goddamn slow. And I found when I did this, I was like, wow, that's really shitty. So what I did was I created another version, and this version, it unpacks using the what do you call it? What is it called? The union. So in colors here, I define color as a union between basically just a standard unsigned integer and a structure broken down into the character components of the colors, the different channels. And you can refer to this data either as a single integer or as one of the 8-bit channel components. So using that, I can basically unpack the data, perform the operation, and then I use the constructor for color to repack it. And I figure this is very succinct. This is a very nice, very elegant way of writing the code. But what would happen if we do it the old-fashioned way? And we unpack by shifting and masking out the top bits. So masking by FF will clear out everything in the higher bits. Then multiplying by A. And then right shifting by 8. I could just put divide by 256, but I figured since we're writing everything here out in bitwise operators, might as well be consistent. And in the end, then shifting the components back into their positions and bitwise ORing them all together. So, like, we would expect for a really good compiler, it should be able to generate identical code for these two identical operations. However, if we actually run the motherfucker, remember that just the standard fade was 5 milliseconds. Now let's run this motherfucker with fade shift. So here we go. Modify the alpha value a little bit there, and let's take a look. And we see that now we are at 1.29 milliseconds. So almost 4 times faster just by that small modification there, by handling the bit shifts ourselves. So this just goes to show that it's always worth benchmarking. You can't assume anything. You can't assume that you're going to do better than the compiler, and you can't assume that the compiler is not going to shit the bed, because apparently sometimes the compiler will shit the bed. And of course, these results are only hold for the Microsoft Visual Studio. If you tried to compile this same stuff in GCC, it might actually be faster using unions, or even the Intel compiler. The Intel compiler is generally the fastest for compiling for x86, so I would imagine it would be able to optimize this code a lot better. But for good old Visual Studio, yeah, it shits the bed for this code representation. So we learned something new, and that is don't use the union access or the constructor to pack and unpack inside of a loop anyways. It's a convenient way to access these members outside of any critical code path. But in a critical code path, you don't want to be using this kind of representation. So yeah, there is our fade in standard code, and we get 1.29 milliseconds. Now comes the fun part. We're going to try to do this in SSE. And it's the same basic principle, which is to say that we want to unpack our components. This is the unpacking part here. And then we want to multiply by alpha, and then we want to shift right by 8. And then we want to repack our components together and store them. So how is this going to work out in SSE? Well, let's take a look. So we'll go to our good old friend, where is it? Fade SSE. Here it is. And yeah, I'm just going to have to explain this now. Shit. This is where I have to do stuff. So the first parts, I hope, are fairly self-explanatory by this point. We want to set one register with alpha values, and they're going to be 16-bit alpha values. We'll get to that reason a little later. And another register, we're going to set it with 0, because we need a 0 register. Then in the body of the loop, we're going to load our source pixels, which we haven't done yet, but it's quite similar to store, except with store you supply the pointer to the address, and you supply the register to be stored. With load, you just supply a pointer, and then the return value goes into the register that you want to load the data into. So we're loading into the source pixels register. And then we have to unpack the values. So first of all, why are we unpacking? And second of all, how are we unpacking? These are the two questions that I have to answer, and that I will answer if I can get my whiteboard up. And then I want to delete this part of the whiteboard and get another thing here. Okay. So the operations that we have to perform are multiply by alpha, and then shift right by 8, or divide by 256, I should say. So we know this is high, this is low. This is going to be called SRC, the source pixels. And the contents are ARGB, 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 ARGB. So here's the contents of our source after we've loaded it. Now, ideally, what we would like to do is, these A's are not important. They're from the back buffer, and they don't mean shit. The alpha that's important is the one that got passed into the function. And so what we would like to do, for example, is we would like to, move the alphas into here. That one doesn't matter, but line them up with the RGB, and then we would like to multiply them down. So we want to use a multiplication operation to give us results here, 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 and here that we can then shift and then store back into the memory. But there are multiple problems with this. The biggest problem is that it's not possible, because the results would not fit into another register. Think about it. Multiplying a 8-bit value times an 8-bit value. How big is the result going to be? It's going to be 16 bits in general. If you've got a general 8-bit, that can be anything from 0 to 255, multiplied by another general 8-bit, you're going to get generally 16 bits of result, ranging from 0 to... who the fuck cares? It doesn't matter. What's important is that you're not going to be able to fit the results into a destination register. So multiplying 8-bit by 8-bit isn't going to work. Second problem is of course, that instruction doesn't exist, multiplying an 8-bit by another 8-bit value to get an 8-bit result. That instruction does not exist because it's not possible. So forget about that. We have to get 16-bit results. Now the problem with that is there is no instruction. I mean, there are weird instructions you can multiply 8 bits by 8 bits. They're not going to work for us. Forget about them. In general, you cannot multiply an 8-bit value by an 8-bit value to get a 16-bit result in your register. How would that work? You wouldn't have enough. You'd have to fit the results into 2 different registers. So what we need to do is we need to expand these 8-bit values so that they are 16 bits wide. So instead of, each register holding a value like OXFF or OXAO, this would be expanded to OX00FF or whatever. Doesn't matter. That's the first thing you're going to want to do. Expand your 8-bit channels to 16 bits so that you can then multiply them together. All right. Where's my code? Here it is. So that's what this is doing here, this unpack low and unpack high, extended packed integer 8. This is the unpack part of the story. Now, what do these instructions do? Well, I'm going to first introduce you guys to these 2 web pages. Very useful. Well, one more useful than the other. You can find them, mainly I've come to these, the Microsoft web pages, just by searching Google for the actual name of the intrinsic. And it'll give you a short description, the form, the actual instruction that the intrinsic translates to, and then an algorithm that shows you what the intrinsic is doing. So fairly useful, and I use this mostly when I was learning. Recently, I've come across this web page. It's much better. This one gives you an algorithm and a description. It also tells you what version of, what CPU ID version you need to be able to run the instruction. And it tells you what include file you need, and so forth. And quite important for later on when you're really getting into the fine-tuning, it tells you the latency and the throughput of the instruction. This is important, but not right now. I'll come back to this topic later on, but it's not important for right now. So the Intel thing, the Intel webpage gives you a way better way to search for instructions and gives you better description. But you might need to use them both. One thing I would caution you about is that sometimes the names of the intrinsics are different between the Microsoft and the Intel. Mostly they're almost all the same, but I believe a few of them are a little bit different, so you have to be wary about that. But in general, I would recommend using this web page to search for whatever. You can search by name of intrinsic, you can search by name of instruction, or you could maybe search by other things that I'm not sure about. You could also filter by whatever technology you're interested in, and by categories of instructions. Okay, so what does packed, oh wait, this is multiply. I actually want unpack low epi. Well, it doesn't matter. Well, it interleaves the lower 8 signed or unsigned 8-bit integers in A with the lower 8 signed or unsigned 8-bit integers in B. So we're interleaving integers, which is interesting. But you might think, first of all, well, how does that work? How does that unpack things? What's the correlation between interleaving and unpacking? And you might also look at this and be like, I don't really understand what's going on here. So that's why I Googled this, because it's going to be way better than any diagram that I draw. So this is what the instruction that this intrinsic translates to is this instruction here. And this is what it does. So it takes unpack low EPI8. So the EPI8 part means we're going to be working with 8-bit packed integers. Now the low part means we're going to be working with the low 64 bits of each of these registers. So we take A and we take B and we interleave them like this. So the first byte of A goes into the first byte of the destination. And then the first byte of B goes into the second byte of the destination. And then the second byte of A goes into the third byte of the destination, and so on and so forth, interleaves them. The reason why we have low and high is because if you're interleaving, you can only fit half of A and half of B into the destination because you're going from 2 registers into 1. So that's why you have a high version and a low version. And yeah, so this will interleave. Now, if you set B to 0, what you're going to get is you're going to get the bytes of A going into the low part of every 16-bit integer, and the bytes of B being zeros, just filling the high half of every 16-bit integer with 0. So this will, if you set M2 in this case, or B, if you set it to 0, all this is going to do is unpack the bytes in M1 so that they become 16-bit integers in the destination. So if you want to unpack, you need to have zeros to unpack with. It becomes a little more complicated when you're working with signed integers. If you have signed bytes in here, then depending on whether the number is negative or positive, you're going to have all zeros or all ones in here. But that's complicated, and we won't be covering that because it's not very useful for us. But just know that this unpacked instruction, although it is mostly used for unpacking, because you're interleaving stuff, it could also be used for other things. But mostly we'll just use it for unpacking. And that's how it works. So getting back to our code, we're going to unpack the low half of our pixels into register named source low 16 and unpack the high half into source high 16. So this is the low end. So this would be 3G3 R3. And after where's the center line? So here's the center line right here. Between the high 64 bits and the low 64 bits. And if we, let's see which one of these is this one. So now if we go so unpack low will give us what? It's going to give us right, B0, and the top half is going to be all zeros. R0, G0, R0, R3. There we go. So there's I fucked it up. Whatever. You know what? I don't care. Unpack high. I should have switched to a different layer for this one, but it probably won't hurt me too much in the long run. So here's what we get after we unpack. We got these 2 registers here, which hold the 16-bit values of these channels. Now, we're going to multiply them by alpha. Now, alpha has already been prepared for us because we did set 1 with our alpha into this register here. So we have a register and all the 16-bit values are filled with alpha, which is, you know, a value between 0 and 255. So the top 8 bits of each of these packed 16-bit values they're all set to 0. All right. So next step is to multiply these registers by alpha. So we're going to multiply 2 packed 16-bit values together. Now here's the problem. We can multiply. There are instructions for multiplying packed 16-bit values together. We have this. It is possible. However, the thing about multiplying two 16-bit values together in general is if you multiply OXFFFF by OXFFFF multiplication, your result is going to be, correct me if I'm wrong, but I believe it's going to be it's going to be FFFFFFE. This will be your result. That was dyslexia there, wasn't it? There we go. So the result, again, the same problem we had with bytes, they aren't going to fit into the destination registers. This is a problem. However, in our case, well, first of all, the way this is handled by SSE is that there are two instructions for multiplying 16-bit values together. Now, there might be more, but there's two that we are going to be aware of for the time being. And I have created a diagram for this because I am prepared. But in order to show the diagram, I'm going to have to hide a bunch of other shit. So we'll hide this, hide that. And then we're going to show this diagram. So in general, when you want to multiply two 16-bit integers together, your result is going to be 32 bits. There are two instructions, mul low and mul high. Now mul low, mul high, they do the same operation. They multiply these two together. But mul low puts the low 16 bits into the destination, the position in the destination that corresponds to the positions or the position of the two sources. So multiply the first packed integer in A and the first packed integer in B, and the result goes into the first packed integer in C. Which part of the result goes in depends on which instruction you're using. You use mul low, you get the low 16 bits in here. If you use mul high, you get the high 16 bits. Now, because we're multiplying values where the top 8 bits are 0, our result is actually going to end up being, well, let's just see. Let's say our color and our alpha are both FF. So OXFF, wait, let me, OX00FF times OX00FF. So our result is going to be EFFF0000. So the top is going to be zeros anyways. Who the fuck gives a shit? So we use mul low for the case where the top 8 bits are all 0, and then we get the exact result. There's no truncation or anything. So yeah, we can use the mul low in order to multiply two effectively 8-bit values to get a 16-bit value, as long as you extend your 8-bit values before you perform the multiplication. And that's what we do. So let's go back to, that's good, that's good, that's okay. Well, I feel like we're missing something. Yeah, that's what we're missing. And also, that's not it. That's not it. Ah, that's it. I think that's all we need. All right. So, multiply these ones together and take the low 16 bits of the result. So we'll use mul low, which is what we get here. Mul low 16 and mul low 16 for the unpacked low part and the unpacked high part. We're multiplying them by alpha. And I don't think we need diagram for the rest of this because it's really simple. Once we have that 16-bit value. Then we shift right by 8 bits on both sides. Let's draw it. Let's be R1, 1, 1, and 0, 0, 0. Here we go. So here's our 16-bit results of the multiplication. So the next thing that we want to do is shift right by 8 bits. By 8 bits. And what that'll do is that'll just take these high 8 bits, shift them over. It's the same as dividing by 256. And the result is going to be, and then RGB. And the same will be for here, so I'm not even going to write it. But you get the general idea. So we go, let's see here. Right. So now we shift by right. We shift right by 8 for both of these. And finally, we have to combine the high and the low together, repack them into 8-bit values. Because obviously the graphics card is not going to understand 16-bit values for the back buffer, for the pixels. It needs them packed back into 8 bits. So we use the packus, which is pack unsigned with saturation. And that will pack our values back into 8-bit values. G1, B1, R0, G0, B0. And what pack does is very simple. What it actually does is, where is it? Let's go packus. Now we have to find the green one. Here it is. So convert packed 16-bit integers from A and B to packed 8-bit integers using unsigned saturation. Now, saturation means, well, unsigned obviously means we're treating them as unsigned values from 0 to 65, 5, 35 or something. I don't know, whatever. And saturation means that, let's say the value here in these 16-bit, if it's greater than, so if value is greater than 255, then the result is going to be 255. So it doesn't like wrap over. It doesn't just ignore the top 8 bits and store the bottom 8 bits. It if the value is greater than what can fit in a byte, it's just set to the maximum that can fit in a byte. That's what saturation is. And if you had signed, then it would also go in the opposite direction. If it was less than the maximum or the minimum that could fit in a byte, it's set to the minimum. But since we divided all of our values by 8, there's no way that they're going to be greater than 255. So the saturation doesn't come into play. All it means is that we take the low 8 bits of each of these 16-bit packed integers and fill them into here. So this would become B0, G0, 2, 2, 1, 1, 1. There. And that's the final result of all of our calculations. And then this is just stored back into memory where we loaded the original source pixels from. So you can just like normal functions, you can nest intrinsic in functions within each other. And I see a lot of people writing code like that, but it is more difficult to read in most cases. I do it here mostly just to show that it's possible. But I often prefer just setting them, giving each intrinsic operation its own line. And you'll see that actually looks nice when you look at the decompilation or the disassembly. But yeah, you can, they work a lot like normal functions. The only difference between an intrinsic function and a normal function is normal functions are in libraries. They're not part of the compiler itself. An intrinsic function is built into the compiler executable. Just like the operation of incrementing a pointer or incrementing or adding two integers together. You don't need to link to a specific library in order to do that. The compiler just knows what kind of code to generate for that operation. And the same way, the compiler just knows what kind of code to generate for an intrinsic function call. That's really the main difference between intrinsics and normal functions. But anyways, I'm getting off track here. So that's the whole shebang right there. You load your source, you unpack it into two different registers holding the 16-bit, the bottom 2 pixels and the top 2 pixels. Then you multiply them by alpha, divide by 256 by shifting right by 8, and then you pack them all together into a single register, and you store that back in memory. So let's see what performance we can get. Our optimized version of the C code gave us 1.290 milliseconds. Let's go fade SSE build. Start, and we get, just as before, we get the same result, same effect, so there's nothing wrong with our code logic. And yes, log file was updated. Let's see what we got. So here we get about 250 microseconds. So a little bit of quick math will show us that this is about 5 times faster than what we get with our standard code. That's a 500% increase in speed. That's pretty good. And it's about what you would expect when you think about it. Because with a single operation, looking at some of our other things that we've got here. Jesus Christ. Yeah. So with a single operation, we're basically processing 6 channels at a time. So we would expect, about 6 times increase, but you never get like your full. There's always, diminishing returns and all that bullshit. So a 5-fold increase is about what you would expect. And that's what you get. Oh. All right. So let's just take a look at the disassembly of this. Decal spec no inline. And we're going to see just what it looks like. Shouldn't be too much in the way of surprises. So we'll go to the disassembly. So here we're setting up our loop variables. We're setting up our registers that we're holding our constants, alpha and 0, in here. And here's the body of the loop. And as you notice, the intrinsics, they basically they boil down to more or less one instruction per intrinsic. So here's our load, and it translates into a move. Here's our unpack low, unpack high, unpack high. So you see that these two, unpack low and unpack high, translate into 3 instructions, 2 unpack instructions, and a single move to just fix things up. Because like I said before, our intrinsics can take 2 sources and 1 destination. But the actual instructions, one of the sources is also the destination. So that means that the compiler has to sometimes insert some extra moves just to make it all work. And that's one of the beauties of using intrinsics. You don't have to worry about that bullshit. So yeah, more or less say one instruction per intrinsic thing here. Multiplication, again, mul low translates into p mul w. Shift right translates into p shift right, or shift right logical word. And pack translates into pack. And then store translates into move dqa. And then here you have your loop variable, increment the pointer, compare it with the end, and then jump if they're not equal. Or jump, I don't know what JB means. Jump if, I don't know what JB stands for. Whatever. Jump if we are still less than that. At any rate, there you go. Very simple. Very straightforward. And a huge performance increase by using SSE. All right. So another thing to be mindful in optimization is taking advantage of special cases. Oftentimes, special cases, you can cut corners and execute them faster than you would for the general case. So the general case of fading by some kind of alpha value, you can have special cases where you're just fading by, for example, half. If you just want to reduce the color, I guess, the brightness by half, basically by using the alpha value of 128 or 127, somewhere around there. That's a special case, and that can be optimized. Let's say alpha, we're going to fade by half. So alpha is going to be 128. Now, if we revert our equation back to its proper form, which was, or no, not its proper form, but the form we have, 256, divided by 256. 128 divided by 256, multiplying by 128 and then dividing by 256 is equivalent, identical, to multiplying by 2, which is identical to shifting right by 1. So instead of doing the whole circus where you multiply by alpha and then you divide by 256, you can just directly divide by 2 and save yourself a whole lot of hassle. You can save yourself a multiply, right? Multiplication is a non-trivial operation, not as slow as division, but it's still slow. Oh yeah, I wanted to do a thing, and I'm going to do it right now because I just remembered it. Fade. Fuck you. Fade shift. So our good old friend fade shift. I'm going to go to definition. And let's try dividing by 255 just to see how much slower it is. So this is the optimized version that doesn't use the union access, uses just shifting. The version that divides by 256 via shifting gave us about 1.29 milliseconds of performance. So let's see what the version dividing by 255 gives us. 255 is a more accurate result. So if there is no difference, we would prefer to divide by 255. But as we can see from these results, it is almost twice as slow. Not quite, but almost twice as slow to divide rather than to shift. So if we change this to just by 1, just fudge the numbers just a smidge, we can see that performance is much better. I just wanted to show that off there just to make sure that you can see that there is an actual tangible benefit. So by doctoring our results and giving us about 0.4% error, we can increase the performance by almost 200%. Which in my books is totally worth it. All right, so getting back on track here, we want to do fading but only by half, so that we don't have to do the multiplication. We can just divide by 2. So here's what that looks like in SSE. You see, it looks very similar to what we had before, except here we have multiplication, here we have no multiplication. Instead of shifting by 8 bits, we're only shifting by 1 bit now. So let's see what this performs like. Now, if you recall, the normal version did it in about 250 microseconds. So let's see how fast we can do it here. See, I can't adjust the alpha. I'm hitting the scroll wheel. It's not changing because it's fixed to half, or 128. Now we can go to, where is it? Log file. So we're down to 192 microseconds, which is better than 20% increase in speed. So that's not bad, right? That's pretty good. But we can do better. Now you might be saying, hey Chili, why are you even bothering to unpack this bullshit if, I mean, the whole reason for unpacking was we wanted to multiply the values together. We could only multiply in 16 bits, but we're not multiplying. We're doing shifting. So there isn't any reason why you shouldn't be able to shift by 8-bit boundaries, shift packed 8-bit numbers, except for one reason, and that is that instruction does not exist. I've got selected here all the SSE versions, and I typed in shift right logical. And here you go. This is all you get. And as you can see, there's no 8-bit version of the instruction. If I go shift right algebraic, nope, only 16 and 32, and logical shift, only 16, 32, 64. And there's 128, but this one's special. We'll talk about it some other day. It doesn't shift by bits. It shifts by 8 bits at a time, so it doesn't work for us. But anyways, the deal is we can't shift packed bytes. It doesn't work. Here's what would happen if we tried it. I mean, we only have the smallest shift we have is shift 16. Imagine you have 2 packed bytes side by side. The values are 3 and 3, and you shift right. What are you going to get? You're going to get a 1 in here, which is correct. 3 divided by 2 is 1 when you round down. But for the for the lower byte here, what's going to happen is the low bit is going to get shifted into the lower byte because we're shifting on 16-bit boundaries. So there's no barrier between here and here, and the byte or the bit shifts over, and the result here is not 1 but 129, which is completely wrong. Now the good news is, if we're clever, we can get around this. What we can do is, with a small little fix-up, we can shift packed bytes. Because the problem is this one bit that leaks in from the neighboring byte. We don't want this bit to leak. So what we can do is, if we're shifting an 8-bit number to the right by 1, we know that the result is going to be, well, let's call it x. All right. So let's say we don't know what the bits are, but we're shifting an 8-bit number to the right by 1. We know that the very left bit is going to be 0, and the rest are going to be, we don't know. So we always know that this bit has to be clear if we're shifting right. So what we can do is we can create a mask that keeps all the bits except for the top bit of every byte, because we know that this one always has to be 0. So we can just clear this one out by using an AND mask. Logical AND with this mask will mask out the top bit. And so in case the bit leaks from the neighboring byte, it'll get masked out and we'll just get the proper result. So this mask will be, it's going to be OX, and it's going to be F7, so 7F. So if we fill an XMM register with 7F, 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 we can and mask, and then we can simulate 8-bit shifting. And because we use this mask, it doesn't matter which shift instruction we use. We could use a 64-bit shift, 32-bit, or 16. Doesn't matter. So that's what we do here. We do the packed shift. So I create a shift mask up here, and I just do that by set1 packed integer 8 bits. So I fill a register with the byte 7F repeated. And then I load, I shift right on 16-bit boundaries, then I AND with our shift mask, and then I store. So this is a lot shorter than this. So let's see what kind of results we get. This one was 195-ish maybe, 195 microseconds. Let's see what our packed version does. I mean, they're both packed, but this one is packed more. This one's packed with 8 bits. So fade half packed SSE. Let's see what we get. Start, we still get the same value. We shouldn't get any difference in here. And if we look at the results, now we're at 150 microseconds. So that's 100 microseconds faster than the general case in SSE. Not quite double performance, but getting close. Maybe a 40% increase or 40% lower execution time. Execution time? Yeah, I said that weird. What do you got? You got a problem with that? All right, so there's our good version of that. Now, let's just look back for a second at our unoptimized version, because we've been neglecting it, and it feels a little lonely. So fade half. Well, if we do it the old-fashioned way with the union, we know it's not going to be pretty, but let's just take a look. So fade half. Build that. All right. And take a look at the values. And yeah, so it's like, it's faster than the other one. The other one was like, I think about 5 microseconds. This one's 4.26, or 5 milliseconds. This one's 4.26 milliseconds. So it is faster. It's not that much faster, and it's still goddamn slow, because the compiler is, as I so often like to say, shitting the bed here. So this sucks. Don't do this. Now, what if we were to do the same thing we did in SSE? Because think about it. We can use any shift we want as long as we use a mask afterwards. So we can even shift the packed values without SSE. As long as we use the mask, we'll still get the same result. So here I take the value at the pointer address, I shift it right by 1, and then I AND that with the shift mask and store it back where it came from. And if I build this, let's see, fade half packed. So let's see how this does. This one doesn't do the shitting the bed thing by using the union or the constructor to unpack and pack, because it doesn't pack or unpack at all, right? Fade half packed. And it does this kind of, this is like this is single instruction multiple data without SSE instructions, just with normal standard x86 instructions. But as you can see, the results are pretty good. They're not bad. They're like 3 times faster than the standard general case. And they're starting to get close to the SSE's general case. They're still worse than the SSE's slowest version, but it's a respectable speed. And nothing to thumb your nose at. Now, let's see what else I want to talk about here. All right. So what we might want to do is compare this fade half packed to fade half shift, because we have the fade half version here where we use the union to unpack and unpack. But what if we didn't use the union? How would that compare to the this version here? And this is where things get interesting. So let's try fade half shift. Now we can't expect to do better than the packed version because it's just a simple shift and mask. Fade half shift. But we'll expect to do quite a bit better than the shit the bed version. So we're going to start, let's just take a look. So our packed version did 379 microseconds. This version does 380 microseconds, the exact same speed, which is not to be expected. Now let me show you something else that's freaky. It'll blow your mind. Maybe not. I'm gonna go fade half packed, fade half shift. I'm gonna call them both. And then I'm going to put a breakpoint here and here. Now I'm going to start. Now it should do the thing that I'm hoping it would do. Alright, no. Alright, so it stopped on this breakpoint here for fade half packed. Continue. Stopped here again. Strange. Continue. Stopped here again. Why is it only stopping here? It's never stopping here. Let's remove that breakpoint, go again. And now it's not stopping at all. Stop the program. Sure. And the breakpoints are gone. So what the hell? I set a breakpoint here and here, but it only ever triggered this one, even though I'm calling both these functions. Now the answer to the question is that the compiler will actually generate identical code for these two routines here, these two functions. So the compiler is smart enough to see us unpacking these values, shifting right by, just basically unpacking them and then shifting them right by an extra 1 bit, and then repacking them. And it's saying, actually, what you actually want to do with all this is you just want to do this. So I'm just going to do this. So it is super smart when it comes to figuring out this bit shifting bullshit, but it is super dumb when it comes to figuring out this bullshit. So go figure. It's just a weird thing with the friggin' compiler. And I thought it was interesting, so I showed you. Actually, what I'm going to do, just to to basically beat this dead dog. That's not the expression. I forget the expression. Beat a dead horse or something? I don't know. Anyways, so we're going to set a breakpoint here. Oh, wait. No. Because I got both of these here. So we're just going to do that. So we're going to set a breakpoint here. And yeah, we look at the code. Sure. And we see it's basically here. We're shifting right by 1. We're ending with our mask, storing, and then loop. Load, shift, mask, store. So exactly what we wrote is what's being done here. And stop. Now we're going to do it the other way. We're going to comment this one out. Uncomment this. We're going to go to game. We're going to uncomment this. Comment this. Build. Start debugger. Yeah, sure. Go to disassembly. And here you see it's doing the exact same thing. It's loading, shifting, masking, storing. Even though the code is completely different, the end result is the same, and the compiler can see that, and it can make your code much faster. I mean, if it were to do this the dumb way, it would load, and then it would shift and mask into this variable here, shift and mask, and then shift back, or together and store. But it can reduce that to the very simple shift and mask once. So sometimes the compiler is smart and sometimes it is dumb as rocks. That's all I wanted to show here. Now, I'm going to show you one more thing. We can actually make the SSE version a little faster even. And the way we do that is with a little instruction called average EPU8. So what average does is it takes the average of the values in the registers and so adds them together, divides by 2. So what we can do is if we load one of the registers with 0, we're adding source plus 0 divided by 2, which is just source divided by 2. It allows us to divide 8-bit values by 2 without, doing this shift and mask bullshit. So now we can do it in one instruction instead of 2 instructions. Even faster. So what we do is we go fade half, average SSE. Build that motherfucker. Remember, we had 150 microseconds for the last one, I think. Let's see what we got now. We're going to load our log file. 143, 44, 139. So best we can do is 140, I guess, around. So a little bit faster. You can't really improve much because when you remember, just the operation of just repeat storing was like 125 microseconds. So you're not going to be able to do much better than that, especially when you have to load and store in this one. But there you have it. Very nice stuff. And I think that is all we're going to do in this episode. Next episode, we're gonna keep moving on with other slightly more complicated operations as I introduce more and more stuff about SSE. But until then, adios.